Hello everybody, hope you have a great Thanksgiving break. Welcome to this recording of the end of 6.3 and all of 6.4. Wanted to give this to you in case you had to be out of class over Thanksgiving break, totally understand. But we've still got to plow through the little bit of material that's left. So let's go ahead and get started on that. So the first example we're going to look at is this idea of compressing the logarithms. So in other words, we want to smush them together. So how are we going to smush these logs together? First rule is log rules only work if there's no number in front. So we've got 5, we've got -6. Minuses are okay, but definitely no 6. So our first step is to use the power rule of log to put these in the power. So I get, this is log base 4 of x, nothing to do there because there was no number out in front. Now we get plus log base 4 of y to the 5th. And now minus, I can get rid of that 6 by stuffing this into the numerator. Sorry, not the numerator, stuffing this into the power. Now I have logarithms with no numbers in front. Now it's pretty straightforward just to use the log rules here. The power rule, or the product rule, is going to say this is log base 4 of x times y to the 5th goes in the numerator. The minus on that last term is ultimately going to put it in the denominator. And so we get log base 4 of x times y to the 5th divided by x plus 1 to the 6th. Big thing I want to note, because I see this a fair bit, there is nothing we can do about addition inside of a logarithm. So that x plus 1 just stays x plus 1. There's no like trick to get rid of it or anything like that. All right. So now let's do one that's a little bit more tricky. And the reason why this is tricky, the thing that a student, or I would see students likely to mistake, is this minus would get stuffed in the denominator. That's the correct thing to do. But once that gets stuffed, there's a tendency to want to put everything else in the denominator too. So remember, if it has a plus on it, it's gonna need to go in the numerator, unless you've got something really, really weird happening. Wouldn't see that here, but don't want to say it could never, ever happen. But put everything together. My personal recommendation, if you see a log problem like this, is order everything from plus to minus. So all of the things that don't have a minus sign get to sit in front. Everything that does have a minus sign has to go to the back. And the reason to do this is now you're significantly less likely to make that mistake where something that was supposed to go upstairs goes downstairs, or vice versa. First, let's deal with these powers. I can only use log rules if there's no numbers in front of the log. So this is log of b plus 1 to the power 5 minus log of a cubed minus log of c squared plus 1 to the 7th. So now we're in great shape. We have no numbers in front of the log. We can apply log rules. And so I'll explain what's happening, but I'll write the answer like how I would expect you to do this, which is anything with a positive gets to go on top. And the reason for that is because of the product. The product rule says I can staple these two together inside of the log. And now I have one logarithm here. I subtract off this log. Well, I can use the quotient rule just to stuff that in the denominator. And the idea is I repeat that one more time with that term on the far right there and get c squared plus 1 to the 7th also going into the denominator. And so that's how you contract a log. Basically, biggest thing I would worry about is make sure you're rearranging terms. Make sure you know what's supposed to go in the numerator and what's supposed to go in the denominator, because that's the quickest way you're going to lose credit. Next thing we're going to talk about is the change of base formula. So what is that? The idea is if you have a favorite log base, which most mathematicians and engineers do, it's the natural log, then if you have some other log going on, some different base going on, you could always turn that different weird base into the one that you like. And that's using this change of base formula here. So this says for any real number m, b, and n, and actually there's a typo here, these should be little n's. So for any numbers like that, if you have some base b, but you would rather this be in base n, then log base b of m, this base you want to go to, is the base that you have of big M divided by log base n of the new base you want to convert to. So all you have to do to get from one log to another, from one base to another, is to just divide by the log of the old base of the new number, just like this formula says. So as an example, evaluate log base 65 of 13 using the change of base formula. So we need a calculator for this. But the idea is our calculator doesn't have a log base 65 button on it. So we say, well, why don't I either use the common log, which is base 10, or the natural log, which is base e. Those are both on the calculator. And I'm going to use the natural log because it has less letters. So what I'm allowed to do is I can say log base 5 of 65 of 13 is equal to the natural log of 13 is the thing I'm trying to find the weird base log of. Divide that by natural log of 65. And now I go and I put this in a calculator. And putting this into a calculator, here it didn't tell us, so we'll just round to 2 decimal places. We get 0.61 roughly. And so that's all there is to change a base formula. We have a few web works on it. Don't expect to see it on the final. It's just kind of explaining why we default to natural log. We don't use like a whole bunch of different bases all the time. Because if you're ever in a position where you need to know log of a different base, you can just convert it to a log that you know. Now it's time to start our very last section for pre-calculus. Exponential and logarithmic equations. So this is the section that answers the question of what happens if you need to know a power of something, like you need to know what power to raise a number to in order to get a number that you need. That's what 6.4 is all about. So we're going to start a little bit smooth and then make things a little bit more complex as we go. If we want to solve exponential equations, one way we can do that is getting a common base if we don't have one, or if we're lucky enough to get a common base. Just notice we said exponential functions are 1 to 1. So then if you have any algebraic expressions s and t in any reasonable base, then if you have b to the s equals b to the t, well then you have two exponentials that are equal. What happens is their powers have to be equal. So for example, if 5 to the x plus 1 equals 5 to the 2x minus 3, then you can conclude that x plus 1 equals 2x minus 3. So this happens because the exponential function is 1 to 1. If I have the same outputs, s is in the power, t is in the power, and I get the same number, then actually I must have had the same power to begin with. So we keep going. I'm going to minus x from both sides. 1 equals x minus 3. Move this 3 over, plus 3, plus 3. And I get x is equal to 4 as my final answer. Okay, so x equals 4. We can always go back and test, plug it into the original equation. 5 to the 4 plus 1 is 5 to the 5. 5 to the 2 times 4 minus 3. 2 times 4 minus 3 is 8 minus 3 is 5. So in both situations, I get 5 to the 5. You can always double check you got the right answer. So how about 9 to the x plus 1 equals 3 to the 3x minus 4? So I'd like to use this rule up here, but these don't actually have the same base. Unless I change this a little bit, unless I be a little bit clever about this. In other words, I say 9 to the x plus 1 is actually 9 is equal to 3 squared. And now I use a rule from algebra. I use the exponent laws here. If I have a to the power of n times a different power m, I can multiply those powers. So what that tells me is this is equal to 3 to the 2. Be really careful. You need to multiply the entire power, x plus 1. So that's 9 to the x plus 1. Now I can set both sides equal to each other. I'm going to go ahead and distribute that 2 right here. 3 to the 2x plus 2 equals 3 to the 3x minus 4. So my two exponents are equal to each other. And so I get 2x plus 2 equals 3x minus 4. And I just go ahead and solve this like a normal equation. So minus 2x from both sides, minus 2x. I get 2 is equal to x minus 4. Add 4 to both sides. 4. I was thinking ahead to the final answer. So 6 equals x is our final answer. And we could always double check. If I plug 6 into this, on the left side I get 9 to the 7. Based on our rule that 9 was 3 squared, that's 3 to the 14. Over on this side, 3 times 6 is 18, minus 4 is 14. So the powers match. That's just a way you can check to make sure you got the right answer. I wanted to do one more that involves a trickier power this time. So 9, 3 squared, not too crazy. But here I want to remind you of another rule that shows up a lot, which is if you have 1 over a to the n, so in other words, you've got a power, but it's stuck in the denominator of something, you can rewrite that as a to the minus n. So why is that helpful? Well, I've got a weird power here, 1 to the 25. That's super, super strange. So what I can do is I can instead say 1 over 25 to the 3x minus 1 equals, well, first, 25 is 5 squared, but that 25 is also in the denominator, so it's a minus 3x to the minus 1. And now I multiply the two together, I get 5 to the minus 2 times 3x minus 1. And ignore that right there. One more time equals 5 to the minus 6x plus 2. Now, once again, I have a common base. And this is just a matter of solving. 5 to the x minus 2 equals 5 to the minus 6x plus 2. But now the bases are equal, which means the powers have to be equal. X minus 2 equals minus 6x plus 2. No clean way to do this where we're not going to have to divide, so I'm going to add 6x to both sides. 7x minus 2 equals 2. Gives us add 2 to both sides, 7x equals 4. X equals 4 over 7. So we could go back and plug in and be a little bit difficult, but it's doable to see that we actually get the same answer. It should be 5 to the 1 over 7 in both cases. Except 1 over 25 is going to be a little bit weird because you'd have to do that conversion to check. But that's our answer. All right, next solve. 3 to the 2x plus 1 equals 8x. So we're kind of out of luck now. There's no way to convert 3 to 8, at least not in a clean way. You technically can do it with a weird logarithm, but that's essentially doing what we're going to do right now. So when you can't match bases, what should you do? We should take the natural log of both sides. You can take any log you want, but natural log is usually the easiest. Main reason why mathematicians do that is because ln has the fewest letters of all the logs. Honestly, why we do that. Very lazy. So here, 3 to the 2x plus 1 equals 8 to the x. I say the natural log of 3 to the 2x plus 1 equals natural log of 8x. And why do we take the natural log of both sides? The reasoning is now, if I look, I can solve for these powers up here. So I can say 2x plus 1 is in the exponent, but it's in the exponent of a logarithm. So I can put this over here on the left, natural log of 3. Same thing on the right side, that x can go ahead and come down. And now I have saved x from the exponent. This is the power of logarithms. This is what they let you do. So when we desperately need to invert an exponential, we can do it with the power of logarithms. And now the algebra here is a little bit tricky, maybe not the most intuitive. At the end of the day, I would like to solve for x here. This x is attached in parentheses to a natural log of 3. This x is attached to a natural log of 8. So what I'm going to do is I'm going to get only x's on one side. Get only x's on one side. And then have everything that's not x on the other one. And so this natural log of 3, it looks kind of intimidating, but it's just a number. So we say this is 2x natural log of 3 plus the natural log of 3 is x natural log of 8. And now the intuition is, here's an x, here's an x. This doesn't have any x's at all. So what I'm going to do is I'm going to move this guy to the other side. And what that's going to do is, on the left side, I'm only going to have natural log of 3, which is confusing, but it's just a number. Close parentheses over there. I get x to the natural log of 8, not to the, times natural log of 8, minus 2x natural log of 3. And the rationale behind doing that is now, all of a sudden, I can factor an x out. That's the whole intuition behind getting that on its own side. But now natural log of 8 minus 2 natural log of 3, I don't know what that is, but it's a number, so I can divide by it. So I'm flipping sides a little bit here, but I can say x equals the natural log of 3 divided by the natural log of 8 minus 2 times the natural log of 3. And whatever on earth that number is, I could plug it into a calculator if I needed to, but that's our answer to this question. This would be an exact answer. If this problem said round to 2 decimal places, you would put this in a calculator, and that would be your answer in that specific case. Let's wrap up a few more of these exponential equations and move on from there. Exponential equations aren't too bad. It basically just boils down to, if you can't get a common base, take a natural log of both sides. We could take a natural log right on this first example, 30 equals 5e to the 2t minus 2. Or we could be a little bit smarter about it, divide both sides by 5 and simplify first. So I get 6 equals e to the 2t minus 2. Now I take the natural log of both sides, natural log of 6 equals natural log of e to the 2t minus 2. And now what happens? On the left, I get natural log of 6. Here I get 2t minus 2 times natural log of e. But something happens here. Natural log of e. Natural log, the base of natural log is e. So when the base is the same thing as what's inside of the log, this guy is just equal to 1. So what I can do then is I can say the natural log of 6 equals 2t minus 2. Add 2 to both sides, get 2t equals natural log of 6 plus 2. So I plus 2 to both sides here. And then I round it all out with t equals natural log of 6 plus 2 divided by 2. And there's no like simplification I can do there, because natural log of 6 isn't divisible by 2. It's not even a rational number. So that's the best that I can do there. One more example, and that'll be it for exponential functions. You might notice it's really, really short, so something suspicious is going on here. Solve 4 to the 5x minus 2 equals 0. Sorry, equals minus 1. What's going on here? The answer is no solution. B to the, let's just say z. Z could mean anything here, is always greater than 0 for any b. I can never raise a positive number to a power, at least a real power, and get a negative. It's just impossible. So we would have discovered this. How would we have known without just spotting it? The way we would have known that is I could go ahead and try to solve it. So that's what I'll do over here in red. Get natural log of 4 to the 5x minus 2 equals natural log of 1. But this does not exist. That's what D and E stands for. This does not exist, because we said you can't have log of a negative number. You can't have log of 0 either. So then this is an equation with no solution. So the second half of 6.4 says, what happens if your variable happens to be stuck in a log? It's not the most common thing in the world, but it can happen, especially if you insert a log where it might not belong to help you with something else. And so for that, we can use a similar fact, which says, if you want to solve a logarithmic equation, you can boil it down to an exponential equation instead. So if I have log base b of s is equal to something, well, from our log section, that means I'm asking what power do I need to raise b to get s? C. And so I can solve a log equation basically by solving an exponential equation. So let's start. Let's do 2 examples. Solve 6 log base 3 of x minus 4 equals 8. So this rule we talked about only works if the log is by itself. I can't just kind of magically convert it when there's stuff around. But that's not a big hurdle. I can isolate the log. We do this a lot. Whenever we have something with variables, we get it by itself. 6 log base 3 of x equals 12. Now I can divide both sides by 6. Get log base 3 of x equals 2. Now I can make the conversion. So this example says use this rule. If I'm being honest, the way I think about it is, if I have log of something is equal to a number, then I'm always allowed to raise it to whatever the base is. I can raise it to anything. And so I can say if log base 3 of x equals 2, then I can exponentiate both sides. I can say 3 to the log base 3 of x equals 3 to the 2. But now by cancellation, if I have 3 to the log base 3 of anything, that's just whatever's on the inside. So I get x is equal to 3 squared. X is equal to 9. So that's how I think about it. You can convert it using this form, but I always just imagine it feels cleaner to me to say exponentiate both sides, take 3 and raise it to the 2 sides you have. I feel like that makes things cleaner. So let's do another example where the numbers are a little bit dirtier. So solve 3 plus 2 natural log of x equals 17. To do that, I'm going to subtract 3, move 3 over. I get 2 times natural log of x equals 14. Divide by 2. Get the natural log of x equals 7. And now how do I solve this? I'm personally going to say e to the natural log, e because natural log is log base e, equals e to the 7. And so then our final answer is x equals e to the 7. So not a clean number. If this problem said round to 3 decimal places, we would put this in a calculator. But here e to the 7 is our exact answer. This would be the exact no error solution to this equation. One thing I need to say before we move on is for logarithmic equations, you always need to check for what are called extraneous solutions. So what an extraneous solution is it looks like it works on first glance, but when you try to go back and plug in, it causes a domain error. I didn't do that here, to be honest, because I didn't remember it first shot, but let's go ahead and do that now. I go back and I plug in, and I get 6 log base 3 of 9 minus 4 equals 8. This is a 9. And the only thing you're worried about is a domain error. It's not going to happen that you can plug the number in and the numbers just don't work. What's going to happen is you try to plug in something, but it turns out to be negative really sneakily. So this is okay, good solution. And just to be 100% sure, what's happening is 6 times 2 minus 4 equals 8. You can check the numbers match, but as long as you can plug into the log, it'll be okay. Same thing down here. I have x equals e to the 7. So I say 3 plus 2 natural log of e to the 7 equals 3 plus 2 times natural log and e cancel equals 17. So that's a good solution. We've checked for extraneous solutions. Logarithmic equations can have extraneous solutions. Be on the lookout for that. Let's do one more short one. 2 times log base 4 of x plus 1 minus 5 equals minus 3. So what this problem is trying to get you to learn is don't freak out if the inside is not just x. Solve just like you were, stay the course. And what happens is when you exponentiate both sides, you might have a tiny bit of algebra to do at the end, but nothing crazy. So for example, for this problem, I'm going to add 5 to both sides. I'm still going to get the log by itself. That's my number one goal, number one priority. Log base 4 of x plus 1 equals 2. I can divide both sides by 2 and get log base 4 of x plus 1 equals 1. So that's what I've got so far. Now what I'm allowed to do is I can say 4, the number I'm choosing to raise, by the way, is always just the base, because then it'll cancel. So 4 to the log base 4 of x plus 1 equals 4 to the 1. But now 4 and log base 4 cancel, which was by design. That's what we wanted to happen. That was our scheme the whole time there. So x plus 1 equals 4. Subtract 1 from both sides. X equals 3. So now we check, does that work? Again, the big thing we're worried about is, do I have a domain error? Am I actually plugging in something negative and not noticing? That sounds weird. How would that happen? We'll see that it can happen. But here I go, I plug in. 3 plus 1 is 4, so this just says 2 minus 5 equals minus 3, which is a true equation. So we plugged in, we checked for extraneous solutions. X equals 3 is a good solution. New example, now it's everybody's a log. And so now we have to do a little bit of footwork to solve this, because if I exponentiate both sides, I'm going to have e to the, or 10 to 1 power minus another. And I'm not going to be able to cancel using log rules like I can't say e to the a minus b, where both are logs, has any special rule. So what am I going to do? Here I need to use properties of logs. You might look at this and say, well, why don't I just use quotient rule, which works. So I can say log of x plus 3 over x is equal to log of 11. And in practice, there's nothing wrong with doing this. You can still solve the equation normally. But there's an important thing we've learned in our class, which is fractions are kind of stinky. Easy to get messed up with fractions. So what I'm going to do is I'm going to make sure all my logs are positive before I solve this. And I'm going to move this log to the other side. Get log of x plus 3 equals log of x plus log of 11. Now I can combine without any gross fractions around. So happy day on that one. Now I apply a rule here, which you might guess what could happen. I raise both sides to the 10. 10 because this log doesn't have a base on it. And so what that means is the base is actually 10. I get x plus 3 equals 11x. Subtract x from both sides. 3 is equal to 10x. So then x is equal to 3/10 or 0.3. So once again, I go ahead and I plug in, I try, and I see if this works. Log of 3/10 plus 3 minus log of 3/10 equals log of 11. And then you could combine this if you want. This is log of, using log rules, 3.3 over 0.3. And here I should be careful not to write equals because I don't know if they're equal yet. But this is equal to log of 11. Just by dividing, 3.3 divided by 0.3 is 11, which is exactly what I was supposed to get. So I erased that to write it down again. But the idea was I started on the left, worked my way over to the right. And so now I've confirmed that this isn't actually an extraneous solution. So everything I'm doing in red here is I'm checking to make sure there are no extraneous solutions. I'm checking to make sure nothing breaks when I try to plug these numbers in. Feels weird, but the next example will show you that these things really do exist. And here it is. the last new example. Solve log base 8 of x minus 1 plus log base 8 of x minus 3 equals 1. So let's put everything together. So first is, I'm adding two logs together. I would like to do some sort of exponentiation here. I can't do that with two logs, but I can do that by combining these logs. So x minus 1 times x minus 3. So I combined logs. And now because I have base 8, I can say 8 to the log base 8 of x minus 1 times x minus 3 equals 8 to the 1. So in other words, I'm left with the equation x minus 1 times x minus 3 equals 8. Here it might be a little bit rusty on solving quadratic equations. How do we do that? Well, when this side isn't 0, we have some work to do. We have to FOIL. So let's FOIL. I get x squared minus 3x minus x. Two minuses make a plus 3 equals 8. Going to do two steps at once here a little bit. Minus 8 to both sides. I get x squared minus 3x and minus x make a minus 4x. Minus 5 equals 0. Now what I do is I factor x minus 5, x plus 1 equals 0. You can also use the quadratic equation if you'd like. Either way, I get the solutions x equals 5 and x equals minus 1. We go back and we check for these extraneous solutions, which we're starting to believe might not exist, might be mythical, but let's check. So I check x equals 5. I get log base 8 of 5 minus 1 plus log base 8 of 5 minus 3 equals 1. Log base 8 of 4 plus log base 8 of 2 equals 1. You could plug this into a calculator, or you could just do one more step, the same combining step we did earlier. Log base 8 of 1 equals 1. Sorry, log base 8 of 8 equals 1. So yeah, we have another good solution here. So, all right, if it's not this one, then extraneous solutions must not exist. So let's test. I get log base 8 of minus 1 minus 1. Aha. We can actually stop here. Log base 8 of minus 1 minus 1. Log base 8 of minus 2, which is undefined. You can't put a negative in a log. So in other words, I'm going to take this, and this x equals minus 1 has to go. Because when I go back and try to plug it in, it's undefined inside of that log. It gives me log of a negative. Why did that happen? It happened in this combining step right here. So if I plug minus 1 into this step that the pink arrow is pointing at, I get two negatives inside of the log, but they multiply to be a positive. That would be okay. Problem is, this came from two separate logs added together. So it kind of breaks apart. It doesn't plug back in like it used to. So when you're checking for extraneous solutions, all you really have to check for is something like this doesn't happen where you're plugging in a negative. As far as exam goes, if you do this, you just plug in and you get positive numbers every time inside of the log. You can stop there. You don't actually have to prove the two things are equal to me. I'm just looking to see that you know what you're looking for, that these things actually plug in the domain. So what I'm trying to get at is, for this problem, you could have stopped here. On checking for extraneous solutions would have been fine. Same thing for this problem. You could have stopped down here. Everything inside of the logs was positive. One more example here, just check, just make sure anytime a number appeared inside of a logarithm, it was really a positive number. Doesn't always happen, like we saw here. On the exam, I'd be very suspicious of us math professors that we're going to put one that has a negative answer. But that's all there is to this section. So I hope everybody has a great Thanksgiving break. I will see you all next week.